So we defined in last lecture weak convergence. In this lecture, I want to discuss the principle of uniform boundedness. So let me start with a simple lemma on weak convergence. So let me take X a normed linear space and Xn a sequence of points which satisfies the following two conditions. First, I will assume that this sequence is bounded. So there exists a finite constant C such that the norms of Xn are bounded by C. And then B, I will assume that L of Xn converge to L of X for a family of bounded linear functionals L, which is dense. So let's say that L belongs to set A, which is contained in X prime, and A is dense. And what I claim is that this implies that Xn converge weakly to X. So I just remind you what we are proving. X, it's a normed linear space. We have a sequence of elements of X which are bounded. L of Xn converge to some Lx. So there exists a point X such that L of Xn converge to L of X for all L in a set A, which is dense. And what I claim is that Xn converge to X. So let's prove this lemma. Well, it's very easy. So what we need to show is that for all m in X prime, m of Xn converge to m of X. So fix a positive epsilon. Since the set A is dense, there exists L in A such that the distance from L to m is bounded by epsilon. Now I want to prove that mxn converge to m of x. So let's compare m of xn minus m of x. Well, by linearity, this is equal to m of xn minus x. Now let me add and subtract minus L of xn minus x plus L xn minus x. This, let me bound this. So we have two different linear functional computed at the same point. So this is bounded. So the first term is bounded by the distance between m and L times the norm of xn minus x. This quantity here, it's bounded by the sum of the norms, but xn by assumption are bounded in norm. So this is bounded by c plus the norm of x. And by assumption, the norm of m minus L, it's bounded by epsilon. So this first term, it's bounded by c plus x times epsilon. On the other hand, the second term, well, by linearity, this is Lxn minus L of x. And by assumption, L of xn converge to L of x. So if I send n to infinity, this converge to 0, which means that the limit sup of this expression as n goes to infinity, it's bounded by c plus the norm of x times epsilon, and this holds for all epsilon, so this means that m of xn converge to m of x, as I claimed, and since this holds for all bounded linear functional m, this is exactly what xn, this means that xn converge weakly to x as we claimed, as it is claimed in the lemma, so this completes the proof of the lemma. So here is the main theorem of this lecture. I'm taking X, a Banach space, and on this Banach space I have a family f alpha of functions defined in X, taking value in R, and these functions I will assume that they are continuous. That they are subadditive, which means that f alpha x plus y, it's bounded by f alpha x plus f alpha y, and that they are absolutely homogeneous, which means that f alpha ax, it's equal to the modulus of f of a times f alpha of x. And also, I will assume that they are bounded in the sense that for all x in X, there exists mx such that, which is finite, such that the supremum over alpha in I of f alpha x, that this is bounded by mx. So here I have a family f alpha for alpha in I, and I'm not assuming anything about I can be uncountable. So I'm assuming here that these functions are pointwise bounded, so that if you fix a point x, then the supremum of f alpha at this point x, supremum in alpha, it's bounded by some finite constant mx. And the theorem states that if all these conditions are satisfied, then there exists a constant c such that the supremum of alpha of f alpha x, that this is bounded by constant times the norm of x. Okay, and this for all x in X. So actually, these functions f alpha are uniformly bounded by c times the norm of x in the whole space. So there exists this finite constant c, such that this supremum is bounded by c times x for all x in the space X. So the proof, you have to recall the principle of uniform boundedness, which was proved 2 lectures ago. There I had a family f alpha of continuous function, which were pointwise bounded, and the conclusion was that there exists a set G, which is open. So this is by the theorem of uniform boundedness, which was proved 2 lectures ago. It stated that under the continuous, that these functions are continuous and pointwisely bounded, that we could extract or find an open set G, and such that this bound was uniform over that set. So this means that the supremum, so there exists this open set C, and there exists a constant m, finite, such that the supremum of alpha of f alpha x, that this is bounded by m for all x in G. And, well, since G is an open set, I can find a point in G it's G, it's non-empty, so I can find a point Y, say, in G, or let me call it Z in G, and since G, it's open, there exists a ball of radius, positive radius, and centered at Z, for which is contained in G. So G contains a ball of radius R, strictly positive and centered at point Z, which is contained in G. So actually, this bound holds in a ball. Well, I don't know where the ball is. So there is a ball centered at Z, which has a radius R. And I know that in this open ball, this bound holds uniformly. Now I want to conclude an information about F on the whole space. So this means that the supremum over all alpha of F alpha Z plus Y, Z, remember, it's the center of this ball, that this is bounded by M for all Y belonging to a ball of center at the origin of radius R, right? I can write any element of this ball as Z plus Y, where Y is an element of the ball centered at Z, at the origin and with radius R. So let me use that ball. So now I want to take a point Y, say that has radius over 2. So this point Y, it's of course inside this ball. And I want to estimate F of Y. And for that, I will use the properties of F of alpha, that it's first subadditive. So I want to estimate F alpha of Y. And the information I have is that Z plus Y is bounded. So let me write F alpha of F alpha Y plus Z minus Z. And then let me use subadditivity for these 2 points. So this is bounded by F alpha Y plus Z plus F minus Z. And of course, F minus Z, by the second property, it's equal to F of Z. And both F alpha of Z and F alpha Z plus Y are both bounded by M. So this is bounded by 2M. So this gives me an upper bound for F alpha Y. F alpha Y, if Y it's a point which has whose norm it's equal to R over 2, then F alpha of Y it's bounded by 2M. Let me now get a lower bound for that expression. So for the lower bound, let me, so for the lower bound, which I will write it here, I will start with saying that Fy plus Z, by subadditivity, this is bounded by Fy plus Fz. And therefore, this means that Fy, there is always alpha, I'm fixing alpha. So this means that F alpha Y, it's bounded below by F alpha Y plus Z minus F alpha Z. And by these inequalities, both expressions are bounded by minus M. So this, this expression, the absolute value, it's bounded by M. The same thing for this one. Therefore, they are both bounded below by minus n, and therefore the sum is bounded by, or the difference is bounded by minus 2m. So we proved that f alpha y it's bounded above by 2m, it's bounded below by minus 2m, and this proves, therefore, what I will write here is that whatever y in x whose norm is equal to r over 2, f alpha of y, it's bounded by 2m, where m is the constant given by the principle of uniform boundedness. So I just kept in the blackboard the two main facts we proved up to now. The first one, which was a consequence of the uniform boundedness principle, is that we could find an open set, so a ball centered at some point which we call z, with a strictly positive radius r, and such that this bound holds uniformly for all alpha in I and for all, well, here is a supreme alpha in I, so I don't need that condition, just that, well, this bound holds uniformly for all x in this open ball. And from this property and the properties of our functions f alpha, we concluded that for any y in x whose norm is equal to r over 2, then the absolute value of f alpha y for all alpha in I was bounded by 2m, where m is this constant, and r is the radius of this ball. Now we are ready to conclude. Let's take a point x in x. We want to estimate f alpha of x, but I can write f alpha of x. So I have informations on points whose norm is equal to r over 2. So I want to transform x into a point which has norm equal to r over 2. So for that, I will first divide x by its norm. Now I have, let me take, I have now a point which has norm equal to 1, and since I'm dividing, let me multiply by the norm of x. Now to get something which has r over 2, let me multiply by r over 2. So now this element y has norm equal to r over 2, and since I multiply by r over 2, I have to divide that. And therefore, I didn't do anything up to now. So now let me use the fact that this function it's absolutely homogeneous to say that the absolute value of this it's equal to 2 times x r f x r divided by 2 times x. So I'm using the fact that f alpha is absolutely homogeneous. Now this is equal to 2 times the norm of x divided by r times the absolute value of f alpha of this point. But as I observed before, this point in x has norm equal to r over 2. And for points which have norm equal to r over 2, the absolute value of f alpha, it's uniformly bounded by 2m. And therefore, what we proved is that the supremum in alpha of f alpha of x, that this is bounded by 4 times m divided by r times the norm of x. And this is exactly what we wanted to prove. We wanted to prove the existence of a finite constant c for which the supremum of f alpha x was bounded by a constant times the norm of x. Here is the constant, which was obtained by the principle of uniform boundedness. So this completes the proof of this theorem. So this theorem is very important. We'll see many of its consequences So let's see our first one. Let's assume that we have X a Banach space and that we have a family L nu or L alpha of bounded linear functionals defined on X. And let's assume that this family is such that for all X there exists a constant f of X such that the supremum for alpha in I of L alpha X, that this is bounded by some mx, by this mx. So here I have a family L alpha for alpha in I. Again, I insist I is not assumed to be countable. So I have this family, and I'm assuming that this family is pointwise bounded family of bounded linear functionals. And this corollary tells you that then there exists a constant C, which is finite, such that the supremum over alpha of the norm of L alpha, it's bounded by constants. So actually, if this holds, if we have for each x a finite constant mx such that this supremum is bounded by mx, it follows much stronger statement is that this family of bounded linear functional is actually bounded. And well, the proof is a straightforward application of the previous theorem. Let me just define f alpha of x to be the norm of L alpha of x. And what I claim is that this family f alpha satisfies the assumption of the previous theorem. So let's see what were the assumptions. The first is that they were bounded, they were continuous. So f alpha were a continuous function. But, well, that's clear because L alpha, it's a linear function, and in particular, it's continuous. Then we needed f alpha to be subadditive. So let's prove that f alpha defined this way, it's indeed subadditive. So let's take f alpha x plus y. By definition, this is L alpha x plus y. And this is, well, this is equal because L alpha is linear to L alpha x plus L alpha y. Now, this is bounded by the sum of L alpha x plus L alpha y. And this is equal to f alpha x plus L f alpha y. So this proves that indeed the function f alpha defined by this equation is subadditive. Now we need to show that it's absolutely homogeneous, which means that f alpha ax it's equal to the absolute value of a times f alpha x. And here again it's very easy. So let's consider f alpha ax. By definition, this is the absolute value of L alpha ax. By linearity of L alpha, this is a L alpha x. But this is equal to the absolute value of a times the absolute value of L alpha, but this is f alpha x. So that proves the third property of this family f alpha. And now the last property was that this family was pointwise bounded, so that for all x we could find a finite constant mx such that the supremum over alpha of f alpha x is bounded by mx. But this is exactly the assumption we are imposing on this family L alpha, right? The absolute value of F alpha, it's equal to the absolute value of L alpha. So this condition follows trivially from the main condition of the corollary. So with this definition, we have that all the hypotheses of the previous theorem are satisfied. Therefore, by the previous theorem, we know that there exists a finite constant C such that the supremum of alpha of F alpha x, that this is bounded by constant times x. But by definition, F alpha, this is equal supremum in alpha of L alpha x bounded by constant times the norm of x. Well, but that means, and this holds for all x in x, so this means that if I fix some alpha, what I have is that the absolute value of L alpha x is bounded by C times the constant. So this implies that the norm of L alpha is bounded by C. And this C is the same for all alpha, so that the supremum in alpha of the norm of L alpha is bounded by C. And this is exactly the thesis of our corollary. So we proved that there exists a finite constant such that the norms of these bounded linear functionals are bounded by these same constants. So here is a second corollary. Now I'm taking X, a normed linear space. Observe that I'm not assuming here anymore that X is a Banach space. I'm just assuming that X is a normed linear space. And I'm assuming that in this space X, I have a family X alpha, alpha in I, which has the following property, is that for all bounded linear functional L, so for all L in X prime, there exists a finite constant CL such that the supremum over alpha of L of X alpha, that this is bounded by this constant CL. So the assumption is now on this bounded linear functional. I have this family of elements of a normed linear space, this family X alpha, and I'm assuming that whatever the bounded linear functional, there exists a finite constant CL such that the supremum in alpha, this set I, of L of X alpha is bounded by CL. And what I claim is that, well, from this assumption it follows that this family of points, of elements of X, is actually bounded. So what I claim is that there exists a C such that the norm of X alpha, it's bounded by this constant C for all I alpha in I. Why is that useful? Well, assume that you have a family X alpha converging to a point X. That will imply that these, since weakly converging means that the functional converging, that will imply that these family are bounded, and from that we will conclude that the sequence is uniformly bound. So it will follow from this result that if you have a sequence xn weakly converging to x, then it must be, it is bounded. But that we will see in a second. Let me first prove this theorem, and let me insist on the fact that I'm not assuming X to be a Banach space, but just a normed linear space. So let's go to the proof. The proof, it's a very simple consequence of the previous corollary. And, well, first observe that we have seen already that if we have X a normed linear space, then the dual space, X prime, it is complete, and therefore X prime is a Banach space. So this is the first observation, is that, well, although X is not a Banach space, X prime is complete, and therefore X prime it's a Banach space. Then a second observation is that, well, we have X, X prime, and X double prime. And we know that we can embed X in X double prime by associating to a point X in X the element of X double prime Lx, which is defined as follows: Lx of L, so L is now a bounded linear function, it's an element of X prime. Lx applied to L, it's equal by definition to L of X. So with this definition, we can embed X, the set X, in X double prime. And moreover, we have that the norm of Lx, it's exactly equal to the norm of X. So this is the second observation needed in the proof of this corollary, is that, remember, we can embed X in X double prime by this relation. And we have, moreover, that the norm of this bounded linear functional is exactly equal to the norm of X. Now, let me consider the family Lx alpha. So this family of Lx alpha, it's a family in X double prime, and it's acting over a Banach space, the Banach space X prime. So I want to apply the previous corollary to this family, considering this family as a family of bounded linear functional acting on a Banach space, the Banach space as X prime. So to apply the previous corollary, what I need is that for all L, I need that the supremum in alpha of Lx alpha applied to L. So for all L, I need a constant C of L, finite, such that the supremum of alpha in I, of Lx alpha of L, to be bounded by constant in L. That was exactly the assumption of the previous corollary. Well, but this assumption follows directly from the main hypothesis of this corollary, because by our definition, Lx of L, Lx alpha of L, it's exactly equal to L alpha, L of X alpha. So we have that indeed, by assumption, the supremum of alpha of Lx alpha, it's bounded by CL for finite constant CL. Therefore, we know that for all L in X prime, there exists a finite constant CL, such that the supremum in alpha I, and alpha in I, of Lx alpha, so this family of bounded linear functional defined in X prime, is pointwise bounded. Well, so by the previous corollary, it follows from this relation that there exists a finite constant C, so that this family of bounded linear function is actually bounded, so there exists C such that the supremum for alpha in I of the norm of Lx alpha, that this is bounded by C. Well, but now if you recall the identity between the norm of the bounded linear function of X and the norm of X, we have that the supremum, so this implies that the supremum for alpha in I of X alpha, it's bounded by that constant, and this is exactly what we wanted to prove. We wanted to prove the existence of finite constant C for which the norm of x alpha is bounded by C for all alpha, and this is exactly what we proved by using the previous corollary. So I anticipated a bit in the previous lemma or the corollary what I had in mind. So here, consider X a normed linear space. Consider a familiar sequence Xn of elements of X. Assume that Xn converge weakly to some point X. Then I claim that this sequence is bounded. So that the supremum in n of the norms of Xn, it's bounded. Or it's so remember the first lemma in this lecture was telling you that if you have a sequence which is bounded, and if, well, Lxn was converging to L of x for all L in a dense set, A, then we could conclude it from the boundedness of Xn that actually Xn was converging weakly to X. Well, here, it's some sense of a converse result of this first one is that saying, well, if we know that Xn converge to X weakly, then the norms of this sequence is bounded. So the supremum in n of Xn is bounded. And the proof, well, it's an elementary consequence of the previous one. So what I claim is that the hypothesis of the previous corollary, it's in false. So let's take L in X prime, so a bounded linear functional. What we need to show is that there exists a finite constant CL such that the supremum in n of L of Xn, that this is bounded by CL. This is what we need to prove. So let me consider Lxn. Well, we know that Xn converge weakly to X. This means that this sequence Lxn is converging to L of X. So L, we have a sequence of real numbers, L of Xn, converging to a real number if we are working on the fields of reals, or complex number if we're working on with the fields of the complex. Well, since this sequence is converging to that one, to this point, this element, this complex number, this real number, it means that it's bounded in norm. So this means that the supremum in n, that this is bounded by some constant C, which of course depends on L. And this is exactly what we needed to prove. So by the previous corollary, so this implies by corollary 2 that the supremum in n of Xn, that this is bounded by a constant, so that there exists a constant C0 such that the supremum of Xn is bounded by C0, and this is exactly what we wanted to prove. And we shall use this corollary many times. So just keep in mind that if you have a normed linear space, so I'm not assuming it's a Banach space, and we have a sequence which is converging weakly, then this sequence is bounded in norm. So let me conclude this lecture with a proposition. X is a normed linear space. We have a sequence Xn converging weakly to X. We have seen that Xn is bounded, this sequence is bounded. What I claim is that the norm of X, it's bounded by the limit imp of the norm of Xn. So this sequence, the norm of Xn, it's bounded. Well, we don't know if it's converged or not, but it's bounded. So what I'm claiming is that the limit imp of this, the norm of this sequence, it's an upper bound for the norm of X. So let's prove. So we have this element X in X. we know that there exists L in x prime such that the norm of x is equal to Lx. And here, L has norm equal to 1. So we have seen that we can find a bounded linear function L whose norm is equal to 1 such that the norm of x is actually equal to the absolute value of L applied to x. Now, we know that xn converge weakly to x. Since xn converges weakly to x, this means that L of xn converges to L of x. Therefore, if I take L of x, this is equal to the limit in n of the norm of L of xn. And the norm, the absolute value of L of xn, it's bounded. So this quantity, it's bounded by the norm of L times the norm of xn. So this sequence, it's bounded by this one. Therefore, its limit, it's bounded by the limit inf of this sequence. Right? So we have a sequence, and this sequence, it's bounded by another sequence, which means, and this implies, that the limit of this sequence, it's bounded by the limit inf of this sequence. I'm not sure that, well, this limit may not exist, but the limit inf exists, and the limit inf, it's larger or equal than the limit of that sequence. Now, the norm of L, it's equal to 1. So this is equal to the limit inf of the norm of xn. And the norm, the absolute value of Lx, it's equal to the norm of x. So we have that the norm of x, it's less or equal than the limit inf of the norm of xn, which is what claimed the proposition. And this is also a very useful result which will be used many, many times. So with that, we conclude this lecture.